Hello friends, Mr. Burrell here. We're in Unit 3 talking about polynomial functions. We just finished talking about the fundamental theorem of algebra and complex polynomials. So we're going to extend that a little bit, continue to talking about different characteristics of polynomial functions. Specifically today we're going to talk about identifying intercepts and end behavior. And we'll talk about what that is. Today, let's see if I can get my pen working here for us. So by the end of this lesson, by the end of this video, this is what I want you to be able to do. Identify intercepts and positive and negative intervals of a function from its graph. I want you to be able to describe the end behavior of a function f of x as x approaches positive or negative infinity. I want you to be able to write a polynomial given the solutions to that polynomial on a graph. We'll briefly touch on that. And I want you to be able to know the basic parent functions of polynomial graphs and draw a basic graph of a polynomial given its equation. So there's a lot in this lesson to cover, so let's dive right in. But these are the objectives at the top of your guided notes so you can keep track of what you should be understanding. So here's some definitions. Most of these you are already probably pretty familiar with. So x-intercepts. When I talk about an x-intercept, I'm going to go ahead and draw a little function over here. When I talk about x-intercepts, the x-intercepts are the x-coordinate of a point where the function crosses the x-axis. So here and here, wherever a function crosses the x-axis, that is the x-intercept because it intercepts the x-axis. A y-intercept is the y-coordinate of a point where the function crosses the y-axis. So this right here would be the y-intercept because that's where the function crosses or intercepts the y-axis. That's a y-intercept. Let me get a different color here. Positive intervals of a function are the intervals according to x where the function is above the x-axis or where the y values or the output values are positive. So this up here would be where the graph is positive. And on the next slide, we'll talk about how we write mathematically those positive intervals. But it's where the function is above the x-axis. Negative intervals are wherever the function is below the x-axis or the y values are negative. So down here, where the y values are negative, that is a negative interval, the interval over which the function is negative or below the x-axis. Now those four terms are ones you should have been kind of exposed to before. This last one, end behavior, is completely new. So when I say end behavior, I'm talking about the behavior of the graph of the function f of x as x approaches positive or negative infinity. So what that's basically saying is, what is this graph doing as x gets really big in the x direction, really big in the positive x direction, or what is the graph doing as it gets really big in the negative x direction? So you'll see here, this graph is going to keep going and going and going, up and up and up. So as x gets bigger this way, y is going to get bigger this way. As x gets really big this way, y is going to get really big this way. So how I would say that mathematically is as x approaches, I'm going to write an arrow, positive infinity. So as x gets really big this direction, y, or f of x, as mathematicians like to write, f of x gets really big this way, or in the positive infinity direction. Conversely, over here, as x approaches negative infinity, or as x gets really big in the negative direction, this graph is going to keep going up and up and up and up and up. So f of x is going to approach positive infinity. So end behavior is just a way of saying as my x value gets really, really big in the positive direction or in the negative direction, what is my function doing? What is my graph doing? And in this case, my graph is going up and up and up to infinity. Okay, let's look at a couple of these graphs and identify each of these different characteristics that we just discussed. So right off the bat, I'm going to highlight in red all of my x-intercepts. I'm going to highlight in blue all my y-intercepts, so anytime I cross the y-axis. I'm going to highlight in green anytime my graph is positive or above the x-axis. but I'm going to highlight in this dark violet color wherever my graph is negative or below the x-axis. And hopefully that will help me to answer some of these questions here. So my x-intercepts, where are they? Well, my x value right here, I didn't want that really. My x value right there is at x equals 1, and my x value over here is at x equals -3. So my x-intercepts are at 1 and -3. My y-intercepts, let's look at the y-coordinate down over here. My y-intercept is going to be at, it's like halfway between -2 and -4, so my y-intercept is going to be at -3. And you notice these points, this point on the graph is going to be 0, -3. 0 in the x direction, -3 in the y direction. This point's going to be 1, 0. 1 in the x direction, 0 in the y direction. This point is -3, 0. -3 in the x direction, 0 in the y direction. So the x-intercepts are the x coordinates of those points. The y-intercepts are the y coordinates of this point right here. Okay, my positive intervals. As it said on the previous slide, my positive intervals according to x, where the function is above the x-axis. So if I'm looking at my x values, so I'm going to look at this x-intercept, because right at this point is where my graph changes from being positive over here to negative under here. And then right again through this x-intercept, my graph goes from being negative to positive again, right? So the intervals where my graph is positive is from -infinity up to -3, because it's positive all the way this way, all the way up until -3, and my graph is positive again from 1 all the way up to positive infinity. So it's positive from here all the way forever into this direction. The graph will be positive. The negative intervals are between those two intervals. So from here to here, from -3 to +1. So my negative interval, written in parentheses, is from -3 to +1. Okay, now let's look at end behavior. So this terminology here says, as x approaches infinity, f of x approaches what? Whereas x gets really big in the positive direction, so as x keeps going this way forever and ever and ever, I should train the color of my pen. As x goes positive in the x direction forever and ever and ever, what is happening to y? Well, y is going positive. It keeps going up and up and up and up forever in the positive direction. So as x approaches infinity, f of x approaches infinity. As x approaches -infinity, so as x keeps going to the left forever and ever and ever, what's happening to y? Well, y is just going to keep going up and up and up to positive infinity. So as x approaches positive infinity, y approaches positive infinity because it keeps going up. As x approaches -infinity, f of x approaches positive infinity because it keeps going up and up and up forever and ever. Okay, let's do one more of these. Identify each of the following in this graph. So I'm going to go ahead and right off the bat, in red, I'm going to identify each of the x-intercepts anytime it crosses the x-axis. In blue, I'm going to highlight the y-intercept. In green, I'm going to highlight every part of the graph that's above the x-axis. And in dark red, I'm going to highlight the whole parts of the graph that are negative or below the x-axis, just like so. So, right off the bat, my x-intercepts are here, here, and here at x equals -3, 2, and 5. -3, 2, and 5. That's where I cross the x-axis. My y-intercept is at y equals -2, because that's where I cross the y-axis. My positive intervals, if I draw lines through my x-intercepts, my positive intervals, my green area, is going to be from -infinity all the way up to -3, because all the way to the left, all the way to right here, my graph is positive. And again, from here, from 5 all the way up to positive infinity, my graph is positive again. So in between there, this is an interesting x-intercept because it kind of bounces off of the x-axis instead of going through. If you reflect back to unit 3.3, you know that means that there's a multiplicity of solutions at that point, so it never actually goes back positive. So I have a negative interval from -3 up to 2. So from here up to here, my graph is negative. And then again from 2 up to 5. From -3 up to 2, and then from 2 up to 5, over that whole interval is where my graph is negative. Now let's talk about end behavior again. End behavior, again, says, as x gets really big in the positive direction, what's happening to y? Well, it's going up forever in the y direction. So as x approaches infinity, f of x, or y, approaches positive infinity. As x approaches negative infinity, or as x keeps going forever and ever in the left direction, what's happening to y? Well, it's going forever and ever in the up, or positive direction. So as x approaches negative infinity, f of x approaches positive infinity. And that's what end behavior is. Again, as x gets really, really big in the positive or negative direction, what happens to y? Okay, let's keep going on to the next section. We're going to skip this next graph. If you're looking at your guided notes, we're going to skip this graph. You can work on that one on your own. So real quick, before we get into this next section, we're going to take a look at some graphs of some parent functions of polynomials. So let's open that up real quick. We're going to look at some of these different graphs and what they look like. So first, we're going to look at y equals x. That's a pretty basic one. That is a line. When I graph y equals positive x, that starts down here on the left and it climbs all the way up to the right. If I graphed y equals negative x, it's kind of the opposite. It starts all the way up on the left and goes down as I go to the right. See that? Up, down. Okay. Y equals x squared. That's a quadratic parent function. This is a parabola, so it starts up on the left here, comes down, and then ends up going up on the right. If I graph y equals negative x squared, it just flips. It starts down on the left and ends up down on the right. Okay? If I graph, this isn't a parent function, but this is a cubic function, y equals x cubed plus x squared minus 1. A cubic function, notice that this is positive x cubed plus blah, blah, blah. It starts down on the left and kind of climbs and wiggles up to go up on the right-hand side. Notice what happens when I switch and select this function that has a negative in front. The negative in front kind of flips completely upside down. So it starts up on the left and goes down on the right. This one started down on the left, went up on the right. This one started up on the left, went down on the right. Coincidence? This is a quartic function, or a degree 4 polynomial. So notice again that this is positive. This is a positive x to the 4th, and it starts up on the left and ends up on the right. Looks kind of similar to this quadratic function, doesn't it? It starts up on the left and goes up on the right. If I put a negative in front of it, it starts down on the left and ends up down on the right. Kind of like this negative parabola, this negative quadratic function. Oh, you know what? I also noticed that this linear function started down on the left and ended up on the right. This cubic function started down on the left and ended up on the right. And then when I made those negative, that negative linear function started up on the left and went down on the right. This negative cubic function started up on the left and down on the right. Why is that the case? What patterns are we recognizing here? So, we're going to talk about the end behavior. When I was saying like up on the left, down on the right, up on the left, up on the right, those things, I was referring casually to end behavior. So we're going to talk about some patterns that exist with end behavior according to these different kinds of functions. So we're going to talk about even and odd degree functions with positive leading coefficients or negative leading coefficients. So an even degree function means that the exponent is even. So x squared, x to the 4th, x to the 6th, etc., etc., etc. Even degree functions with a positive leading coefficient are going to look generically like this. They're going to start up on the left and end up on the right. Little smiley face there. Even degree functions that have a negative leading coefficient are going to start down on the left and end up down on the right. Little frowny face here. Odd degree functions with a positive leading coefficient are also going to end up on the right, like the even degree functions, But an odd degree function is going to start down on the left. So it's going to look something like this. An odd degree function with a negative leading coefficient, like the even function, is going to end down on the right, but it's going to start up on the left. A bunch of little smiley faces there. So every function with a positive leading coefficient, the end behavior is going to be going as x goes towards the right, y is going to be going up. So positive leading coefficient means this side is going to be going up forever and ever and ever. Then with an even degree function, the left is going to be doing the same thing, going in the same direction. With an odd degree function, the left is going to be going the opposite direction. So you'll notice this looks a lot like a quadratic function. So if I have a quadratic function like this, it's going to look something like this. A little bit curvier than that, but it's going to kind of change direction those times, that one time right there. 1, 2. If I have a cubic function, it's going to look something like this. 1, 2, 3. A quartic or a fourth degree function is going to look something like this. 1, 2, 3, 4. Changing directions that many times. A fifth degree function is going to look something like this. 1, 2, 3, 4, 5. Obviously, there are more curves than that, but that's approximately the behavior that is going to be exhibited in each of those different kinds of functions. And you can kind of see that here with the quartic, 1, 2. Cubic, 1, 2, 3. Quartic, 1, 2, 3, 4. Quintic, 1, 2, 3, 4, 5. Linear, degree 1 is just 1 and never changes direction. So that's kind of the end behavior associated with these different types of polynomial functions, and we're going to extend that to some of the different problems that we're going to solve. So what is the end behavior of this function? This is a cubic function, which means that since this has a positive leading coefficient, this is positive out in here, which means it's going to be pointing up on the right, and since it's an odd function, this is an odd number, it's going to be pointing down on the left. So it's going to look something like this, right? 1, 2, 3. That's approximately what that function is going to look like. If I graph that on a graph, it would be lots like smoother, you know? But that's approximately what that function is going to look like. So as x approaches infinity, as x goes to the right, y goes up, just like that. So as x approaches positive infinity, f of x or y also approaches positive infinity. But as x approaches negative infinity, so as x goes this way, y goes down. So as x approaches negative infinity, f of x approaches negative infinity. Let's double check that on our graph. Let's make sure we're not crazy, right? Here is that function that I just, oh, not that one. Here is the function that I just did, x cubed plus x squared minus 6. Indeed, it starts down on the left and ends up on the right. Down on the left, up on the right. Now let's look at number 2 here, negative x to the 4th plus 4. This is an even degree function, so I know it's going to end the same direction where it starts, and since this is a negative coefficient, that means it's going to end off pointing down. Since it's an even degree function, it's also going to start off pointing down. Since this is a degree 4, I'm going to have 4 little marks here. 1, 2, 3, 4. So it's going to look something like an M. When I graph that on a graph, it's going to look much more like, I don't know, like this, a little smooth M. So my end behavior, as x approaches infinity, as x goes this direction, y is going down. So as x approaches positive infinity, f of x or y approaches negative infinity. As x approaches negative infinity, or as x goes this way, y goes down. So as x approaches negative infinity, f of x or y approaches negative infinity as well. So that's how you can determine the end behavior of a function without even necessarily needing to graph it in a graphing calculator. To double check ourselves, we'll check in this calculator, make sure that we're not crazy. And indeed, as x goes this way, y goes down to negative infinity. As x goes this way, y goes down to negative infinity. Okay, now the last little bit we're going to talk about, finding and drawing polynomials from their solutions. So if I know the degree of a polynomial function and I know what the solutions are, I can draw a rough sketch of what that function would look like and know what the x-intercepts are and the positive and negative intervals and the end behavior. So it says draw the graph using the zeros or the x-intercepts, analyze the graph for the needed information in each question. So it says over which intervals are the following functions positive, over which intervals are the following functions negative. Okay, so right here, I have f of x equals x minus 3 times x plus 1 times x minus 4. If I was to multiply all those together, the degree of this polynomial would be 3, because I'd end up multiplying x times x times x, which is x cubed. So this is going to be a cubic function. So I know since this coefficient out here, there's no negative out here, it's positive, I know my function is going to look something like this. Since it's positive, it ends up on the right. Since it's an odd function, it starts down on the left. So in these instructions, it said draw the graph using the zeros. Remember what zeros are when I'm talking about polynomial functions? Well, it's the solutions that I would find if the function was set equal to 0. So if each of these terms was set equal to 0 and I solved for x, I'd get x equals positive 3, x equals negative 1, and x equals positive 4. That means my x-intercepts, or my zeros, are at x equals 3, x equals negative 1, and x equals 4. Well, I know that my graph has to start down over here on the left and end up over here on the right. So approximately, my graph is going to look something like this. Up, down, up. I know I had to end up on the right and start down on the left. So I know my x-intercepts. I can determine my end behavior because as x goes this way, y is going to go up. As x goes this way, y is going to go down. Now let's determine my positive and negative intervals. My intervals where my graph is positive, let me grab another color here. The intervals where my graph is positive is right here and right here. The intervals where my graph is negative is right here and right here. So all of these things I can determine about this function without even needing to graph it in a calculator. I can determine it all just using these intercepts here. Let's look at this one other example. Let me change my pen back. Okay, so I have f of x equals x squared times x plus 5. If I were to multiply all these x's together, multiply these factors, I'd get x squared times x, which is x cubed. So this is another cubic function. And since this number out here is not negative, it's positive, I know it's going to look something like this. It's positive, so it's pointing up on the right. It's an odd numbered function, so it's going to be pointing the opposite direction or down on the left. Now I need to find the x-intercepts, or the zeros. So if I set this equal to 0, then I'd set this factor equal to 0 and this factor equal to 0. X squared equals 0 gives me x equals 0 twice. If you remember back to our last lesson when we talked about multiplicity, that solution is going to pop up twice because of this exponent here. And x plus 5, when I set that equal to 0, I get x equals negative 5. So on my graph, I cross the x-axis here and here. So my function needs to look like this. Well, this function over here had 3 places for me to cross the x-axis in order to do that. But remember here, what happens on a graph when you have a multiplicity of solutions. It's not going to cross through that point, but it's going to kind of bounce, reflect off that point. So since my graph needs to look something like this, it's going to go up, down, bounce off of this point because it had a multiplicity of 2, and head back up again like so. So my function is going to look something like that. So I know my x-intercepts. I can determine my end behavior. As x goes to infinity this way, y goes up, so y goes to positive infinity this way. As x goes to negative infinity this way, y goes down, so to negative infinity this way. And then let me hurry and highlight. This would be all my positive intervals. These are the intervals where my graph is positive. And then these right here would be the intervals where my graph is negative. All that I determined just from knowing about multiplicity, knowing about these factors, knowing about the parent functions of a cubic function, and knowing about these positive and negative intervals. All those intercepts, all those intervals, all those end behaviors we can identify from this function. You might be asking yourself, why do we care about all these different characteristics? So when we're looking at a graph that would represent a polynomial function in real life, the end behavior might represent, as we make this much money, what's going to happen to our cost? Or as we spend this much money, what is going to happen to our production levels? That's what we're talking about when we're talking about positive or negative intervals. Positive might represent profit. Negative might represent loss. So all these different characteristics of these functions are going to be called different things depending on the situation that you're using them in. So that's the end of this lesson. Hopefully each of these topics you are able to understand a little bit better. If you need to review any one of those from the video, feel free to do so. We didn't cover this one as much in this video, so we'll cover that in time. But all the rest of these objectives, read through those, make sure that you feel pretty good about them. I hope that was helpful. Please reach out to me if you have any questions whatsoever, and I hope that you enjoyed that as much as I did.